You can tell because I'm the guy that doesn't have the name badge on, having left it in my lodgings earlier today, apparently. I'm a senior engineer for GemTalk Systems, where I work on the GemStone S9 products, most of them these days. And today I'm going to talk about ephemerons. Last year in Prague, I was having a discussion about ephemerons with Elliot and Miranda, and complaining about certain things and talking about others and asking whether certain aspects were actually valuable, and she said they were. And he said, well, why don't you do a talk next year about ephemerons? Long story short, well, here I am. So, ephemerons, but actually, before we actually talk about ephemerons, we should really talk about what the problem is that ephemerons are trying to solve. And that is the problem of finalization. So in Smalltalk, we have automatic storage management. We allocate objects, but we never need to free them because the system takes care of that in garbage collection. And it might be nice to be able to expand that to other things that aren't just objects in the image. The canonical example of this seems to be an external resource like a file handle. If you have an object that represents an open file, it might be nice to automatically, when nobody's referencing that object that references the file, to actually close the file from the operating system standpoint. This is a problem that finalization is designed to solve. Also, you can use that for some internal things, like if you subscribe to some service inside of your Smalltalk image. For instance, maybe a subscription to get some announcements or something from some other object. It might be nice to not have to unsubscribe yourself before you actually get garbage collected. It might be nice to handle that automatically. So these are the kinds of things that finalization is designed to handle. This has been a recognized need in object-oriented languages from very early days in the 80s. And one of the first things that people tried, a number of languages have tried this, is the finalize message. If the garbage collector discovers that an object is about to be garbage collected, that there are no references left to it, then the object is sent by the system the message finalize. The object cleans itself up however it knows how to do that. And then you're done, and then you're all happy. Well, there's a number of problems with this. One of the problems that was really perceived early on was that it's possible for the object in the process of executing its finalize message, it is possible for it to hand out a reference to itself, which some other object then hangs on to, and now the object isn't going to be garbage collected after all. This is called resurrection. And a number of the theorists in computer science thought that resurrection was a bad thing because they couldn't prove a whole bunch of properties when you had resurrection in the picture. Nevertheless, this has been done by a number of languages, among them Java. So Java, in its initial version, has a finalize message. It has proved problematic. They're proposing to deprecate it in Java, and they've replaced it with some newer things. But in the Java language specification, you'll find this diagram where an object is created, and then in order to be storage reclaimed, it has to work through this state diagram, unless you didn't override finalize, in which case the shortcut of the dotted line can be taken. I won't go into detail about that, but suffice it to say, this was their effort at making sure that an object only got finalized once, even if it was resurrected. Like I say, deprecated. And the newer things in Java are more like how Smalltalk does it. We interrupt this presentation to bring you this brief rant. So I want to talk about this thing. I want to actually complain about this. Now there's a story behind this particular logo. In 1998, 19 years ago, the Smalltalk Industry Council decided that the balloon logo was dated and they wanted a new Smalltalk logo. So they had a contest to replace it. Now I thought and still think that the balloon logo is just fine. But my wife's a graphic designer and the prize was $1,000, so hey. We entered the contest with this and we won. Got $1,000, bought ourselves a couple of nice Palm Pilots, because that was the handheld you could get in 1998. And a nice shirt. But I like to think clearly about Smalltalk. I really try to, understand it as a language so that I really, because I think that will help me do good designs in Smalltalk. And this thing I have some problems with. It kind of, the Smalltalk objects all the time, kind of comes from this notion that in Smalltalk everything is an object. And this is a saying that I like to call true enough for marketing. But we're mostly engineers. So no. In Smalltalk, not everything is an object. So, if we have in Smalltalk objects, what else do we have besides objects? Well, how about messages?
They are objects.
Ah, thank you. So messages are so important that Alan Kay has said that he wished he had called it message-oriented programming instead of object-oriented programming because everybody focuses on the nouns and not enough on the verbs, which he thinks are very important. So, as Georg points out, you can have instances of message so they can be objects, but all right, this thing here is what in the United States we call a moose. In Europe, this is what we call a moose. Am I talking about this moose? No, I'm not talking about that moose. It's a fine moose, but I'm talking about the animal, the moose. Now, in theory, I could kill this moose and have its head stuffed and hang it on my wall. So the question is this moose equal to that moose? Well, in Smalltalk, we judge equality by equivalence, and we judge equivalence by can you replace one for the other and use them for most of the same purposes. So if I really want something to eat vegetation, this moose is not going to do very well. And if I want something to hang on my wall, awkward. So my conclusion is this moose is not equal to that moose. So although you can have an instance of message, this is a dead stuffed message. It's not a live message. They're not really quite the same thing. And just to be clear, I do not encourage the killing and stuffing of moose. And fortunately, Smalltalk is also humane. We do not kill and stuff messages unless they die of natural causes. And for a message, dying of the natural cause of death for a message is to be not understood. So if the message is not understood, we stuff it into an instance of message and set that as a message does not understand to the receiver of the original message. Now certainly some humans, especially teenage humans, believe that they might die from being not understood. But for messages, this is an actual problem. So if in Smalltalk we have objects and we have messages, what else might we have in Smalltalk that is first class? Well, we have variables. My clarity of thinking about Smalltalk is not absolute yet. I don't have full confidence in it. I thought about it before putting variables in, but they're there. Globals, temporaries, instance variables, all of these things. And what else might we have? Well, there are the things that variables hold, which we often think of as objects, but they're not objects. They're actually a very important part of the language. which is the object reference. So each variable holds one object reference. In fact, Smalltalk is a statically typed language with exactly one type. And that type is object reference, because it's the only thing that a variable can hold. You might hear analogies for an object reference like, oh, it's like a pointer. And that's kind of true from an implementation sort of perspective. But from a language semantics point of view, then really an object reference, it's a channel for sending a message to an object. And more importantly, it's the only way that you can send a message to an object. And sending a message to an object is the only way you can interact with an object. You can't send a message, you can't interact with the object. Don't have a channel, you can't send a message. In fact, Smalltalk syntax now, we've talked about these four things that Smalltalk has, objects plus the other three, the reference, the variable, and the message. You look at Smalltalk syntax and what the syntactic elements actually manipulate. We have these major elements in Smalltalk syntax. We have white space, which is actually an operator in Smalltalk, and a very important one. We have vertical bars, we have colon equals, we have the caret that's used for return, and then we have literal objects like the small integer 1 or the string or. I'm counting blocks as literal objects. Don't know if my clarity of thinking is quite right there, but for today, that's what I'm doing. So what do each of these things manipulate? Well, the white space operator is so important, message sending is so important that they gave it the space as an operator. If you say self space size, you're sending a message to self. So that operates on the message. These are the way you declare variables, so they only operate on variables. Colon equals operates on a reference in a variable because it's modifying a variable by putting a reference into it. The return returns a reference. And literal objects create an object at compile time, but at runtime, they give you a reference. So here we have all of the things in Smalltalk syntax, and none of them deal directly with objects, because the only way to deal with objects is to send it a message. And we can see that the reference appears here quite often, and it's a very important thing. So, we now return you to your regularly scheduled presentation, already in progress. So Smalltalk doesn't send finalize to objects that it wants to finalize. It handles finalization differently. So we have this contract. There's a garbage collection contract. And the contract is that any object which is reachable through some chain of references through the root of the system, roots of the system, may not be collected. Anything else is fair game, because if you don't have a path to it, right? If you don't have a reference, you can't send a message, you can't send a message, you can't interact with it. So you will never notice if it's gone. So might as well reclaim the space. And so that's the basic garbage collection contract. And for a very long time now, Smalltalks have provided the finalization service through a modification to this contract, an exception, if you will, which is a thing called the weak reference. This is a concept that's been around for a while. Weak reference as opposed to what? So I'm going to call an ordinary reference a strong reference, which keeps the object alive. As long as there's any strong reference, path that consists only of strong references from the system roots, it can stay alive. And a weak reference lets the object be garbage collected. It's still a channel to send a message to the object, but it allows the object to be garbage collected. So how does that work? Well, we have, there's a number of ways to package weak references, and the way that Smalltalk is always used is the weak container, typically a weak array. So let's take a look at some examples. Here's a really simple one. We have this weak array here that has two weak references to two objects. The weak array itself is referenced from somewhere up near the roots of the system, and there's a strong reference here from somewhere that is connected to the roots of the system. But this guy is only connected through this weak reference. So, therefore, the garbage collector is within its rights to come take that object away, but not this one. What if we have a slightly more complicated example? We'll stick a strong reference from that object to this object. Well, okay, now there's a path from the roots of the system down to this object up to that object. You can't take that one anymore. What if we reverse the direction of that one? So now there's a path through here, but still the only path from the roots to this object here is through a weak reference. So the garbage collector is still within its rights to come and take this one away. Notice that the garbage collector is never obligated to take objects away. That's not in the contract. You can fire it if it never takes any objects away, but you're not assured of the timing usually. What if we have two weak arrays? So now we have two weak arrays, and this object is referred to weakly by both of them. Both of the weak arrays themselves are alive, and this object is still alive. But the garbage collector can still come and take this one because all of the paths to it involve weak references. So if the garbage collector takes this object away, then what do those references refer to? Because if there isn't no object, you can't really interact with it, and you have to send a message to it in order to interact with it. And if an object reference is a channel to send a message, then this is a semantically illegal situation. And that's the semantic explanation. In implementation terms, you hear things like dangling pointer, memory corruption, crash, things like that. So the garbage collector does not allow this to happen. When the garbage collector takes this away, it atomically, with respect to Smalltalk execution, replaces the pointers with tombstones. And a tombstone is usually a simple object like nil, reference to nil, or reference to the small integer 0, depending on which dialect of Smalltalk you're using. And this must happen simultaneously. All weak arrays that refer to the same object as being referred, you can't replace with a tombstone in one and then later do the one over here. The semantics get very bad when you do that. So the interesting thing about this is, okay, the object is gone, and it's been tombstoned so that our object space is semantically safe. And there's no resurrection possible because the object is in fact gone. Storage has been reclaimed, it's not there anymore. So then the question, well, who does the finalization? If the object itself is gone, you can't send it a message saying finalize yourself. So this scheme requires that objects have an executor. There seems to be a bit of a death motif here with tombstones and executors. But an executor is a separate object with responsibility for handling the finalization for the object that is now gone. In many cases, the default implementation is to make that a shallow copy of the original object, because it has the state and behavior of that original object. Now, having it be a shallow copy of the original object does, in some cases, reintroduce some of the problems of resurrection, in that the actual state you wanted to be gone may actually be in that copy. So, this particular non-resurrection doesn't solve all the problems that they thought resurrection caused in the first place. And some people think that resurrection wasn't that big of a problem to start with. There's not general agreement on that. So anyway, in this scenario again, we have the garbage collection is made tombstones. And then at some time soon after this, soon being a very loosely defined thing, the system arranges for messages to be sent to the weak containers saying, you've had something collected. And then the container has to go and scan through its slots to see where the tombstones are, And then hopefully it has some notion based on the index of that slot where it finds the tombstone as to what the original object was and what has to be done in order to find its executor, so that its executor can take care of the finalization, whatever is needed. Now in VisualWorks, there's a message sent to every container, and then you have to scan through. In Pharaoh 5, as far as I can tell, it seems to scan through every weak object in the system every time there's a garbage collection that collects anything that is weak. Which seems odd. There was a little reference I found to, oh, there's this thing in the VM coming, but I'm not sure what that is. But to the Pharaoh people, and to anybody else who's interested, I highly recommend this paper from 2 years ago by Andres Malouj, who's covering his face, called Linked Weak Reference Arrays, which is a clever scheme for making tombstones into a linked list of small integers of offsets, which saves a lot of work. In one of the products that I work on at GemTalk, we use very large, weak collections as mapping dictionaries that can be up to several million in size, and scanning these things is a significant burden. So that would be an improvement, I think. And in VA, well, VA does it differently. And you'll have to correct me if I get this wrong, because I don't have a copy of VA on this machine, so I haven't been able to check this week. So in VA Smalltalk, there's a thing called weak array that actually isn't. It acts like a weak array. It does a really good job of camouflage. But for every reference removed from the array, and it does put a tombstone thing there, but it then sends a message to the container that contains not only the index of the object that was removed, but the object itself. Which means that the object isn't dead yet, which means it wasn't really a weak array because it's not a weak reference because it's not allowing the object to be garbage collected. So some people sort of like to have used in the past the word weak to mean any reference that isn't an ordinary strong reference. These days, I at least prefer, and whoever wrote the Wikipedia page on weak reference prefers the definition of allows the object to be garbage collected, and I like that because it's a nice simple reference, or simple definition. And the nice thing about VA's scheme is that it allows did my battery just die? Or did I just push the off button? No, it's on. Okay. New microphone, am I okay? Okay, all right. So, the nice thing about VA scheme is that the object can act as its own executor because it's still alive. It doesn't solve or even attempt to solve the resurrection problem, but I'm not sure how big of a problem that was in the first place. But in fact, its behavior is still a bit like an ephemeron. Remember ephemerons? Let's talk about ephemerons. So let's talk about ephemerons. They were first introduced in GemTalk's Smalltalk products, and then in 1997, in the OOPSLA proceedings, appeared, it's 20 years ago next month, I believe, appeared a paper by Barry Hayes about ephemerons, revealing, sort of why you might want such a thing. Incidentally, this is also the one where the Squeak Back to the Future appeared that same year. As I was looking through this for ephemerons, I came across that. The odd thing about this paper is that it does not define what the behavior of an ephemeron should be. It tells you why you might want one, and it tells you how to implement one. Although I have heard a rumor that there was a bug in the paper. So I'm going to attempt today to actually come up with a definition we'll see whether that definition is correct or useful or not. So in the paper, one of the things that it says, the primary advantage that ephemerons have over other forms like weak arrays is that you can implement a property dictionary with them, where you attach properties to an object and possibly without its knowledge. And these properties are kind of like extra instance variables for the object in that they have the same life cycle as the object itself. They don't prevent the object from being garbage collected. When the object is garbage collected, they go away at the same time, that kind of thing. One example would be subscribing to a service, as I mentioned before, like an announcement. So maybe you attach an announcer to the object as a property, that it wants this kind of announcement. So let's look at a really simple example. Some of the cases are really complex, so we're going to start simple and work our way up. So in the ephemeron world, all references are strong, although there are some references and objects, particularly ephemerons, that are treated specially by the garbage collector. And the first object reference in any ephemeron is special. It's called the key. So this is the key object for this ephemeron. And in this case, we've got a reference from the root to the key object and a reference through the ephemeron to the key object. Now, if we were to take away this reference there, then the only reference is through the ephemeron. And at this point now, the only thing keeping this object alive is the ephemeron reference. So now we want to go ahead and do finalization because that's the condition we're looking for. So at this point, the ephemeron, what I call, fires. Oof. And at the moment that the ephemeron fires, which is during garbage collection, it also ceases to become an ephemeron. It's now just an ordinary object with ordinary strong references. And the system arranges, as we did with weak arrays, the system arranges to sometime soon to send a message to the ephemeron. And in keeping with the death motif, the traditional message for this is mourn. And so the ephemeron now receives the mourn message, and it says, oh, I need to finalize my key. And it can do that however it likes, but one good way to do it might be to just send finalize to the object, which knows how to finalize itself. And then once that's done, then the traditional behavior for a well-behaved ephemeron is to nil out all of its slots. And this key object is now not referenced, and therefore the garbage collector can take it away. And usually in most implementations, you could now put another key object into this ephemeron, rearm it so that it's an ephemeron again. It can go through the whole cycle multiple times. Being an ephemeron is a property of an individual object, and you can switch that on and off. It varies by dialect as to exactly how flexible that is, but in general, it is the property of a single object. So let's go to a slightly more complicated case, because ephemerons can have more than one slot. And the first one, as I said, is special. It's the key. And you can have one or many value slots, because they're all the same semantically. I'm only going to give you examples with one, because it gets complicated enough. And of course, that value slot can have a reference to some object. And the interesting thing about ephemerons is that that value object may have direct reference to the key object or an indirect reference to the key object. And so now, if we take the reference, the reference from the roots that doesn't go through the ephemeron, if we take that reference away, then we still want to finalize this because all the references are coming through the ephemeron. So now we have these property objects, and they, in a weak array system, these objects either would have been garbage collected because the weak array would have been referred to them weakly, and then we would have lost our properties, which we don't want. That would be too early. Or, if this was a strong reference, then this would be keeping the object alive that we want to go away. So either the lifetime of the properties becomes too short or the lifetime of the object becomes too long. But with an ephemeron, then actually what happens is that at this point, the ephemeron fires because all of the references to the key object come through the ephemeron. One through the key slot and any number more through the value slot, but no paths that don't go through the ephemeron itself. So once again, it becomes not an ephemeron, it nils with the key and the value slots, which allows all these objects to be unreferenced and garbage collected. And then, how about a more complicated case? Okay, so we've got two ephemerons, and they have the same key object, and there's this property object, and they're both referenced, but the object itself isn't referenced except through either of the two ephemerons. So in this case, I think we do want to fire the ephemerons as well, both of them at the same time for similar reasons as we did with the weak arrays. They won't receive more simultaneously because, that's ordinary Smalltalk execution. But they will hopefully receive it soon and usually in a fairly high priority process. But concurrent applications need to kind of keep this in mind, that it's not atomic, that these things. And you might have this guy sent finalized twice, one for each ephemeron, but maybe there's a different reason for the ephemeron, maybe there's a different message, or there's different aspects that need cleaning up. But it's still fairly clear that it ought to fire in this case. Now the next one is the controversial one. So, all right, so who thinks that the left-hand ephemeron should fire in this case? Who thinks the left-hand ephemeron should not fire in this case? Okay. All right. And of course, that's because there's a reference here to this guy's key. Now, who thinks that the right-hand ephemeron should fire in this case? Okay. Yeah. Okay. Yeah, okay. I thought you would. From our discussion with fire, I knew you thought. So this is controversial. This is controversial.
Yeah, I just wanted to make sure,
Yeah, it is that case. It is that case. So the algorithm in the Berry-Hayes paper actually says that this ephemeron does fire in this case, or does not fire in this case. Okay.
It's true. It's one of those.
It's one of those. This is why I'm giving a talk on it, so that I understand it. But if we consider these property objects to be like instance variables, then we can reason like this, and I think this may have been the reasoning of the people who originally implemented this, is that if this object is clearly alive, and if this object is to be considered as if it were an instance variable of this object, then it contains a reference to this object which keeps it alive. Therefore, this ephemeron does not fire in that case. Once again, debatable semantics. My recommendation is don't do that. But that's, for language theorists, that's not a satisfactory answer generally. And in this case, where we can leave it the same except we take away this reference, now it's pretty clear that even with all of this, both ephemerons ought to fire, right? Okay. So my tentative statement for trying to define ephemeron behavior, the statement that is missing from the published paper that is still the main reference I was able to find about ephemerons, is this. An ephemeron should fire if and only if the only reference paths to its key pass through ephemerons for which its key is the key. Not the most satisfying statement in the world, but possibly better than no statement at all.
Martin, I was collecting definition, and the one I have is an ephemeron is an association which refers strongly to its value as long as the ephemeron key is not garbage collected.
No. that does not describe any actual implementation I know of, or what is described in the paper.
I think that this is the people from scheme that have the definition.
Okay. Yes, yeah, there are, I did run across that one. And I haven't looked at their implementation to see what they actually do. But, yeah, and actually, since there are questions, I will say it is time for questions.
Hi. A couple comments. So, the original name of ephemerons were guardian objects.
Guardian?
Guardian objects.
Guarding.
Guardian objects. And that, to me, gives me an idea that ephemerons, just as weak arrays, are attempts at concretizing a point of view that is somewhat different from what the application is doing. Basically a visibility thing. Let's reify some visibility notion of, oh, when is this visible, blah, blah, blah. And because of that, I wonder, did you ever find an actual use case of that property table that the paper talks about? That was taken from real life?
Yes.
You did?
Yes. I talked to people here this week.
Okay. I'd be glad to talk about that at some other point.
So, yeah, that's the summary. The advantages and differences between the companies can be its own executor and properties. Garrett.
What kind of finalization does GemStone have?
GemStone has ephemerons on transient objects in memory. We currently do not have any finalization on persistent objects.
Because then my next question would have been, in which transaction are they executed?
Right, exactly. And we have a design, but it's complicated. We have a design, yeah, we have a theoretical, something that theoretically works for ephemerons on persistent objects. That ties into the persistent garbage collection. And it's involved with the whole thing where, the problem with garbage collection in GemStone is that we have up to thousands of different virtual machines all operating against the same object space transactionally. And so there's a lot of phases that it has to go through to do garbage collection in order to identify. And it goes through things like possible dead. There's a possible dead set that collects, and then you have to check and make sure nobody's using that one, and they can vote them down, and they can, anyway, eventually you get promoted to really, truly dead, and then you go away. But there's a little point in there where if you tweak some things, you can actually have a point at which you can actually collect things.
What does GemStone do in this debatable case?
Which case?
The one where you said that's debatable.
Oh, the case where the crossing case. I will have to check that because I have not checked that. I believe we do it. I believe we do it according to this. But I will have to check. Anything else? Doesn't look like it.